Today we will be talking of the one-dimensional finite element problems, and in the last class we had seen how to get this potential energy expression. We had shown that the potential energy of a set of one-dimensional finite elements is given by this expression, where Q is a deformation vector given by Q1 Q2, okay, and we had shown that Ke, that is the element stiffness matrix, is given by the expression EA by L multiplied by 1 minus 1 minus 1 1, okay, and the force matrix for the element, this was obtained by summing up the body forces, tractive forces and the point loads, okay. Now what we will see is this expression, this summation is summation of a product of matrix terms. We will try to simplify this and get it directly as a product of matrices, okay. For doing that, what we will do is, let us say if we take any object and this object has been divided into a set of finite elements like this, okay. Let us say this is element 1, 2, 3 and 4, and these are node numbers 1, 2, 3, 4 and 5, okay. The deformations, let us say we call them Q1, Q2, Q3, Q4, and the deformation of this node is Q5, okay. If we write down the deformation matrix for the first element, that will be the matrix Q1 Q2 transpose. Similarly, the deformation matrix for the second element will be Q2 Q3 transpose and so on, okay. So if we have an element EI which is defined between nodes J and K, then the deformation matrix for this element would be given by Qj and Qk, okay. So what we will do is, instead of having these individual matrices, we will write down one global matrix, and that will be the matrix like this: Q1, Q2, Q3, so on till Qn. Your n is the total number of nodes, okay. Let us say this is my node number n. So we will have one vector or one matrix which we will call as the global deformation matrix, okay. So this matrix we will call it the global deformation matrix. So if we have a set of elements like this, that is E1, E2, E3, E4 so on, and let us say if we have m elements and n nodes, our global deformation matrix would be given by Q1, Q2 so on till Qn, okay. This is our global deformation matrix. Now for this matrix, for this set of finite elements, we can say that the element E1 is connected between nodes 1 and 2, the element E2 is connected between nodes 2 and 3, E3 is between 3 and 4 and so on, okay. So this, let us say, table is defining the adjacency relationship between elements and nodes. It is defining the position of different elements and that of the different nodes, okay. We will be making use of this table later on. If we take up the first element and we write down the stiffness matrix for this, the stiffness matrix for the first element is E1 A1 by L1 multiplied by 1 minus 1 minus 1 1. Okay, similarly the stiffness matrix for the second one would be E2 A2 by L2 multiplied by 1 minus 1 minus 1 1, where E1 is the Young's modulus for element 1, A1 is the area of cross section for the first element, L1 is the length of the first element. Okay, similarly if I take the second element, E2 A2 and L2 are the Young's modulus, area of cross section and lengths for the second element. Okay, and so on. This way we can write down the elemental stiffness matrices for each of these elements. Okay, and if you look up this term, the first term Q transpose KEQ, this term, if I expand it out, that is I multiply this matrix by Q transpose and Q. Okay, if I multiply this by Q transpose, that is Q1 Q2, the terms Q1 and Q2 will be multiplying these two terms and then these two terms. Okay, because this will become a row matrix multiplied by this column and then multiplied by this column. Okay, the product of these two will give me a row vector, and that row vector when multiplied by this column vector Q is going to give me a single potential energy term or the strain energy term. Okay, so now what we will do is, instead of writing the individual matrices like this, I will write a global matrix which will look something like this. What I have done is, if I look at this table, the element E1 is defined between nodes 1 and 2. Okay, and I have a total of n nodes. So I will take n by n, I will take an n by n matrix, and in locations 1 and 2, both in the rows as well as in the columns. Okay, that means the first row and the second row, sorry, first column and the second column, and the first row and the second row, I will put the four terms. These four terms are the terms that correspond to this. Okay, that is the stiffness matrix for element number 1. I have taken first and the second rows and the columns and placed the four terms corresponding to this stiffness matrix. Okay, I got four terms here, that is E1 A1 by L1 multiplied by 1 minus 1 1, sorry there is a minus sign over here, okay. So 1 minus 1 minus 1 and 1. So the four terms of the element stiffness matrix for the first element comes or come in these four locations. Okay. Similarly, I will take the second element. The second element is defined between nodes 2 and 3. Okay, so I will take up node row number 2 and row number 3 and column number 2 and column number 3, and corresponding to those four locations I will put these four terms. Okay, these four terms are obtained from this matrix. Okay, that is E2 A2 by L2 1 minus 1 minus 1 1. So these four terms I will put in these locations. Okay, and so on. I will take up the third element. The third element is defined between nodes 3 and 4. So I will take locations 3 and 4 of this matrix, locations 3 and 4 of this matrix, and place the four terms for the element stiffness matrix for the element number 3. Okay. This way I will fill up all these elements, the remaining places will get a 0. Okay. And this matrix is what we will call as the global stiffness matrix. Okay. Okay, any question up to this point? How I have made this global stiffness matrix? Okay. So now if I look at the global displacement matrix, which is this one, and the global stiffness matrix, which is this one. Okay. And if I write down the expression half of Q transpose K Q. Okay, where Q transpose is a global displacement matrix, K is a global stiffness matrix. Okay, basically what I am doing is I am taking this matrix, okay, and I am pre multiplying it by Q transpose and post multiplying it by Q. What is Q transpose? It is a row vector containing Q1, Q2, Q3 till Qn. Okay. So this is going to be a row vector which looks like Q1, Q2 till Qn. This is multiplied by this huge matrix that I have written. Okay, in this place I will get this complete matrix, the global stiffness matrix. Okay, and this is multiplied by a column Q1, Q2 till Qn. Okay, now if I look at this, my first two terms here contain E1 A1 by L1 and minus E1 A1 by L1. Okay, these two terms. All the other terms are zeros. So when I multiply this row by this column, I will get terms corresponding only to these two. Okay, similarly if I take up the next column, I will get terms corresponding to this, this, this and this. Okay, Q1 will be multiplied by this, Q2 will be multiplied by this as well as by this, and Q3 will be multiplied by this. Okay, and then the product of this row with this column, that is going to be multiplied by Q1. Okay, you have to look at this operation slightly carefully. Okay, and if I compare this with this expression that I had, half of Q transpose into KE into Q. Okay, that means half of this row vector multiplied by this column vector. I will again get Q1 Q2 multiplied by these two terms, again that term will be multiplied by Q1. Okay, you can look up the Q1 Q2, this would be multiplied by E1 A1 by L1 minus E1 A1 by L1. Okay, and we have another couple of some terms over here, and this will be multiplied by Q1 Q2 as a column vector. So these two terms multiplied by these two again multiplied by Q1, that is what will be my first term, and we will get the same term when I multiply this row by this column and then multiply that by Q1. Okay, are you able to visualize that? Okay, and then what we are doing is I am summing it up over all the elements. Okay, so if the effect of this summation I am able to get directly by getting this global matrix. Okay, because if I take this row and multiply it by any column, okay, let us say I multiply it by the ith column. Okay, and the ith node will be a part of some particular element. I will get the corresponding terms from this summation. Okay, let us say if I take the element I, which is defined between nodes j and k, okay, then the jth row over here and the kth row, and similarly the jth column and the kth column and the jth row and the kth row, these 4 terms will give me the terms corresponding to the jth element matrices. Okay, so what I am saying is that this thing will be equal to sigma half q transpose k e q.
So EI is of the jth.
Again?
What is EI? The jth element.
This EI?
So
the element EI. The element EI is defined between nodes j and nodes and the node k. Okay, if you look up this table, the element E1 is between nodes 1 and 2, E2 is between 2 and 3, and so on. So if I take EJ or sorry EI, that is between nodes j and k. Is that okay? Okay, so this way if I assemble my global stiffness matrix and I define my global deformation matrix, I will get this expression instead of this summation. Okay, this summation is equivalent to saying half of q transpose k q, where k and q are the global matrices. Okay. So if I take any finite element formulation, any problem which I have defined as a set of finite elements, I can take each of these individual elements, get their elemental matrices, okay, the element stiffness matrices and the deformations, and from these I can assemble my global equations, or I can assemble my global expression by writing this term. Okay, and this is equal to the total potential energy, strain energy in the system. Okay, U is equal to half of q transpose k q. This is the total strain energy in the system. Is that all right? Okay. Now, the potential energy term consisted of another expression which is this q transpose into Fe. Okay. What we will do is, just like we have defined a global deformation matrix, we will define another term which is a global force matrix. Okay. So if we have a set of finite elements like this, let us say this is my element EI between nodes j and k. The deformation of this is qj, the deformation of this is qk. Okay. We have written expressions for the Fe matrix, that is the element force matrix. What we said essentially was this element force matrix will consist of two forces acting at the two nodes. Okay, so this is, let us say, some force F1, or let me say Fi1, and this is Fi2. Okay, so the element force matrix for this would look like this: Fi1 and Fi2. This is going to be the element force matrix for the ith element. Okay. So what we'll do is we'll define a global matrix in which, again, if I take my first element E1, that is, let's say, defined between nodes 1 and 2. I will take the corresponding force terms for the first element and place them in locations 1 and 2. Okay, so F 1 1 and F 1 2. This is my element number 1, this is my node 1 and this is my node 2. This force is what I am calling as F11 and this force is what I am calling as F12. F12 is the force on the second node of element number 1. F11 is the force on the first node of element number 1. Okay. Fi1 is the force on the first node of element number I, and Fi2 is the force on the second node of element number I. Okay. So if my element 1 is between nodes 1 and 2 and element 2 is between nodes 2 and 3, my second term here I will add F21 and third term here will have F22. Okay. This is location number 1, this is location number 2 and this is location number 3.
Forces are also 1D. Forces are also 1D.
Forces are also 1D. In the 1D formulation we assumed everything to be one dimensional. Okay, if you have a two dimensional element, we will see how to formulate that later on.
So here we talk about first node and second node, we don't say J and K.
We have always been doing that. The first node here is node number J and the second node is node number K. Okay. If my first node is node number J, what I will do is I will take up the jth term over here, and in the jth term I will add Fi1. Okay, and in the kth term I will add Fi2. Okay. See, the first and the second node, when I say this is my first node and this is my second node, okay, this is my first node and this is my second node. This is what we refer to as the elemental numbering. Element has a local numbering which is nodes 1 and 2. These are the global node numbers. Okay. This 1, 2, J, K and so on, these are the global node numbers. Now this global node number J corresponds to element node number 1 for element number I. Okay, that means for this element, this node number locally is 1 and this is local node number 2, but global number is J and K. Okay, so when I look at the local matrices, in the local matrix, this is the first force element, this is second force element. Okay. In the global numbering, this will go into the jth location, this will go into the kth location. Okay, this way what I will do is I will take up all my elements and the forces coming on each of the nodes, the forces which are a part of the element force matrix, those forces I will place at these global locations. Okay, so at each of these n nodes I will get a force which will look something like this. Okay. So if I have a set of forces like this, this matrix is what I call as my global force matrix. Okay, what I have basically done is I have taken up the force elements on each of the element the forces on the two nodes of each of the elements and place them on global locations. Okay, and this matrix is what I call a global force matrix. Okay, and now if I look at this term, that is sigma q transpose Fe, you will find that this will be equal to q transpose multiplied by F. Okay, how do we get that? This q transpose is nothing but q1 q2 till qn transpose. Okay, and this F would consist of F11 F12 plus F21, okay, F22 plus F31 and so on. Okay, what I have taken is I have element E1 defined between nodes 1 and 2 and element E2 is defined between nodes 2 and 3 and so on. Okay, so if I take this row, if I take this row and multiply it by this column, Q1 is multiplied by F11, Q2 is multiplied by F12, and these two terms are what I will get if I take the matrix Q F1, Q1 F1. Okay, that means the Q matrix for the first element and F matrix for the first element. If I take these two and multiply them, I will get Q1 F11 multiplied by Q2 F12. Similarly, if I take up the second element, I will get Q2 and Q3 multiplied by F21 and F22. Okay, similarly, if I take the third element, Q3 and Q4 will be multiplied by F31 and F32 and so on. Okay, the summation of all these terms is nothing but the Q transpose multiplied by F. Okay. So this way, by writing the global equation in this manner, the potential energy expression that I had earlier, that is this expression, I can simplify that to, I had pi equal to sigma half of Q transpose Ke multiplied by Q minus sigma Q transpose Fe. This is nothing but half of Q transpose K Q minus Q transpose F. Okay, this is the expression for the total potential energy in the system. Okay, and this has been obtained by writing the global deformation equation, global stiffness matrix and the global force matrix. Okay, any questions up to this point? Okay, a couple of observations about this global stiffness matrix. If you look at these element stiffness matrices, okay, the first thing that we notice is that these element stiffness matrices, they are all symmetric. Okay, 1 1 minus 1 minus 1, 1 1 minus 1 minus 1. Okay, so all the element stiffness matrices are symmetric. Okay, and if you see the method by which we have assembled the global stiffness matrix, okay, we have retained the symmetry because the element stiffness matrices have been placed both as the row as well as column terms. Okay, so if I take up the ith row and the jth row, sorry, ith column and the jth column and the ith row and the jth row, an element defined between nodes I and j will come on the 4 symmetric terms. Okay, so the global stiffness matrix is also a symmetric matrix. Okay, the first thing that we say is this K is a symmetric matrix. Okay. The other thing that we say is that if I have element 1 which is defined between nodes 1 and 2, element 2 which is defined between nodes 2 and 3, element 3 defined between nodes 3 and 4, and so on. That means the element I will be defined between nodes I and I plus 1. Okay, if I follow this sequence, then I will get terms, only 3 terms in any row. Okay, the 3 consecutive terms next to the diagonal. Okay, if you notice here, element 1 is between 1 and 2, 2 is between 2 and 3. Okay, so between 2 and 3 I have element 2, between 3 and 4 I have element 3. If I take up the third row, I will find non-zero terms only in locations 2, 3 and 4. Okay, so this global stiffness matrix will be a banded matrix with a bandwidth of 3. Okay, so this is a banded matrix. Okay, so if I take numbering like this, I will get a banded matrix. Okay, and the bandwidth will be 3 in this case, the width of the band. Okay, however, if I don't do my numbering like this, okay, I say that my element number 1 is defined between node number 1 and 10. Okay, that means I am taking a set of elements like this. This is my element number 1, and instead of saying that this is between nodes 1 and 2, I say this is 1 and this is 10. Okay, and this is maybe some other number 15, and this is node number 2, and so on. Okay, then what would happen is the terms for the stiffness matrix of element 1 will go in location 1 and 10. Okay, these 4 terms won't come like 1, 2 and 1 minus 1 and minus 1, 1. 1 will come here, and this term will go in the 10th column. Okay, and similarly this term will go in the 10th row, and this term will go in the location 10, 10. Okay, and if that happens, this will no longer be a banded matrix. Okay, and this matrix will then become non-banded, but will still be symmetric. Okay, but this will become a sparse matrix. There will be a term here and a term in the 10th row, in the 10th column, that is, but all the terms in between will be 0. Okay, so the global matrix that I have Okay, this K is either it is banded or it is sparse. Okay, and whether it is banded or sparse, that depends on the numbering that we have done. Okay, how we have numbered the nodes. Okay, so numbering becomes very critical on whether it is a banded matrix or sparse matrix. And it's basically critical because for banded matrices we can get very efficient methods for solving banded matrices. Okay, while if it is not a banded matrix and we have a very large system of equation, the system can become complex. Okay, so the numbering that we do, okay, this numbering, the numbering of the nodes, that is very critical.
The midterms is 0.
What do you mean by midterms?
I mean between 2 to 9.
Between 2 to 9, let's say this is my node 2 and this is my node number 9.
No. E1 is defined between nodes 1 and 10.
Yeah,
So corresponding to E1
yeah,
for the nodes 2 and 9, 2 to 9, all the elements will be 0. That's why it's sparse.
corresponding to E1, I don't understand what you mean. So if I look at this stiffness matrix, I'll get a term in this location and I'll get a term in the 10th location. Okay, but I won't get any term in any of these locations. Okay, because this element 1 between node 1 is defined between nodes 1 and node 10. Okay, but between nodes 2 and between node number 1 and let's say node number 2, there is no element. If there is an element between node 1 and node 2, then I will get a term in this location. Is that okay? No? See, if I have an element I between nodes j and k, in that case I will take the jth row, kth row, jth column and the kth column. Okay, in a one dimensional case like this, one node can appear only between two elements. Okay, if this is my, let's say, node number j, it can either appear with this element or with this element. Okay, so one node can appear only in two elements. If I take the first node and let's say if I am calling this the node number 1 and this is connected to, let's say, node number 10, it cannot be connected to any of the other nodes since this is the first node I am taking. Okay, if 1 cannot be connected to any of the other nodes, all these locations will have to be zeros. When will this term be non-zero? Only when there is an element between node 1 and node 3. Only then this term can become non-zero. Okay, that is why between locations 2 and 9, all of them will become 0 because I have taken the first element between 1 and 10. Okay, this I have taken to be my element number 1. Okay, that is why all the other terms will become 0. Is that okay?
Here if we put j equal to, in the previous one,
Here.
put j equal to 2,
Okay,
then we
j equal to and k equal to?
no, I mean somewhere down the element we will get j equal to 10 also. So what is the difference between that and this 10?
I didn't get it. I have taken some element which is between nodes 2 and some other number, let's say let's say 9. Terms for this element will be defined between locations 2 and 9. Okay, so if I take a second row and the ninth row and the second row and the second column and the ninth column, I will get a term here and I will get a term in the ninth column. I will not get a term here. I will get a term here only when I have an element between 2 and 1. Is that okay? Okay, that is why we say that this global matrix is always symmetric and is either banded or sparse depending on the numbering that we have done. If our numbering system is efficient, okay, then it will be a banded matrix with a small bandwidth, otherwise it will be a sparse matrix. Okay, in fact if when you work on, let's say, a system like Patron or any other finite element package, you will find that the system first assembles the global matrices and then it tries to optimize on the numbering. Okay, because the numbering that you might do might be very inefficient. So you try to optimize the numbering and aim at getting a minimum bandwidth. Okay, so at some stage you will find a message coming that minimizing bandwidth, okay, or optimizing bandwidth. That is basically done with the idea of making it a banded matrix with a small bandwidth. Okay, so this is how the global matrices are assembled. Let's take a small example for this. Okay, last time we had taken an example where we said that okay, we had taken a body like this and we had modeled this by two finite elements. And for this first element we said we will take the area of cross section to be 5.25 square inches. For the second element we said it will be 3.75. Okay, basically at this point it is 4.5. So this 5.25 is the mean of 6 and 4.5. 3.75 is the mean of 4.5 and 3. Okay, and I think we have taken E to be 3 into 10 to the power 7 psi. This is also in pounds, and we have taken rho density to be 0.28 pounds per cubic inch. Okay, and for these we have written down the elemental matrices, that is K1 is equal to E1 A1 by L1 multiplied by 1 minus 1 minus 1 1, and K2 will be equal to E2 A2 by L2 multiplied by 1 minus 1 minus 1 1, and this will be equal to E2 A2 by L2. This will okay. So we had derived these matrices. Now if we take the element force matrices, the total body force is the total weight acting, which is rho 1 A1 L1, that is A1 L1 is the volume, rho 1 is the density, multiplied by 1 1. This will be the force matrix on the first element, and the second element will give us rho 2 A2 L2 by 2 multiplied by 1 1. Okay, rho 2 A2 L2, this is the total weight of the second element divided by 2, so we will have half the total weight acting at each of the two nodes. Here also we have half the total weight acting at each of the two nodes. Okay, and if we put in the values, we will get this to be 0.28 multiplied by 5.25 multiplied by 12 by 2 1 1. This would be 0.28 multiplied by 3.75 multiplied by 12 divided by 2, and this will be 1 1. Okay. Now from these matrices, let's derive the global matrices. Okay. If we take this, I'll call this node number 1, this is my node number 2, and this is my node number 3. This is my element number 1, and this is my element number 2. Okay, so I have element 1 defined between nodes 1 and 2, element 2 is defined between nodes 2 and 3. Okay. So now, since I've got 3 nodes, my global stiffness matrix will have 3 terms in it. It will be a 3 by 3 matrix. So if I write down a 3 by 3 matrix, 1 2 3 1 2 3. Okay. The stiffness matrix for the first element, okay, for this first element will take locations 1 and 2. Okay, so locations 1 and 2 would mean this location, this location, this and this. Okay, so these four terms will come in these 4 locations. Okay. Now if I see both these terms, this part is common. Okay, so I'll just leave this outside, 3 into 10 to the power 7 by 12. Okay, so I'll get a term of 5.25 minus 5.25 minus 5.25 and 5.25. Okay, if I take the second element, that is defined between nodes 2 and 3. So the second element will take locations 2 and 3, the second row and the third row and the second column and the third column, and in these 4 locations I'll put these 4 terms. So I'll get this plus 3.75, here I'll get a minus 3.75, minus 3.75 and a plus 3.75. Okay, so this matrix will be my global stiffness matrix. Okay, and my global force matrix will also consist of 3 terms. Okay, locations 1, 2 and 3. Between locations 1 and 2, I'll get the force terms coming from the first element, that is this. Okay, and again between these two, I'll take this as common. Okay, and I'll multiply it by 0.28 into 12 by 2. Between 1 and 2, I'll get 5.25 and 5.25, and for the second element between nodes 2 and 3, I'll get this term of 3.75. Okay, so it will become this plus 3.75, 3.75. Okay, and in addition to this, we have a point load of 100 pounds acting at node number 2. Okay, so this point force will also be added here, so it will become this plus 100.
We'll have to take the factor inside there.
Then you have to take
Okay, you will have to take the factor inside, fine. This term will come inside, that change you can make. Okay, so this will be our global force matrix, and this is our global stiffness matrix. Okay, so this is how we assemble the global matrices. Okay, once we have assembled the global matrices, then how to solve them, that we'll see in one of the subsequent classes. Okay.